In this podcast, I'm going to talk about how to use sinusoids to model real-world like problems. This one happens to be these cute little foxes here. And it says that naturalists find that these predatory animals vary periodically with time. And we're going to assume that this population of foxes vary sinusoidally with time. So that means we could use a sine or cosine equation to model this population variation. So the records, and then, so when you do these kind of problems, it's really important that you understand what the variables are and that you keep track of them very carefully. So it says that records started being kept at time t equals 0. So t is our time in years, and a minimum of 200 foxes appeared at 2.9 years, and a maximum of 800 foxes occurred at 5.1 years. So our independent variable is going to be time in years. So I'm going to put that on these axes here. I already drew the axes. This is time in years. Good thing to write down. And our vertical axis, the dependent variable, is population, number of foxes. So I'm going to call that capital F. Okay. I'm going to start getting some of the information that's given here down on this graph so I have a visual cues about what's going on here. So I'm just going to eyeball this, and I'm going to put 2.9 years here. And the minimum is 200, so I'm going to call this 200. And then the other time that we're given is 5.1. I'm going to put that over here someplace. I don't have to be real accurate about the scale at this point, but I'm just trying to get a picture of this. That's 800 is the maximum, so I'm going to put a dot up here. I know that the sinusoidal axis for this function would be halfway between there, which is 200 plus 800 divided by 2, which is 500. So this is going to be 500. So we're using our graphing skills to make sure we get kind of an accurate picture. So the graph's going to look something like that. And I don't know exactly how it's going to end up, but I'll continue it. I don't know exactly where it's going to cross. I don't know how many, we're not given how many foxes there were at time 0, but the graph's going to look something like this. Okay, so we want to come up with an equation. So we need to know things like the sinusoidal axis. We need to know the C value, which we do know already is 500. The amplitude, we can figure that out from 800 minus 500 is 300. Make sure that 500 minus 200 is also 300. So we have the amplitude of 300. The distance, the period is, well, 1/2 the period is equal to 5.1 minus 2.9, which is equal to 2.2. And so the period is equal to twice that, which is 4.4. Now the way I figure out B for my equation is B is always the normal period, which is 2 pi in this case in radians, divided by the period in our actual situation, which is 4.4, which we could write as pi divided by 2.2. Okay, well that's most of the information. Now I'm going to use this distance right here is 2.9, and that is a displacement from the y-axis of 2.9 for a negative cosine graph. So if I want to use negative cosine to model this, my displacement would be 2.9. Well, now I have all the information I need to write an equation for this situation, which is going to be foxes as a function of time in years is equal to 500 minus, because I'm using negative cosine, minus 300 cosine pi over 2.2 times t minus 2.9. That's my equation. So I did part A. I sketched that graph to get all the information that was useful for being able to come up with this particular equation in part B. And now it wants me to predict the population when t equals 7, 8, 9, and 10 years. So we can make a little chart here. Here is t, and here is f, and where they wanted for some reason for 7, 8, 9, and 10. Okay, I'm going to get out my calculator. I'm going to put this equation into the y equals menu, which is 500 minus 300 cosine pi divided by 2.2 parentheses x or t minus 2.9 close parentheses, close parentheses. Okay, I'm going to graph this. And let's make sure we're in the right mode. I'm doing this in radian, so I want to be in radian mode, which I am. And I want a window that kind of reflects the situation here. So I don't need to go to -10. I'll start at 0. And I'm going to go out, well, our t-chart so far is going out to 10 years. So I think I'll go out to 12, just so I see a little bit beyond that. I'm going to go by a scale of 1. My y minimum can also be 0. My graph is not going to dip below the t-axis, and my maximum, I'm going to go up. I think I'll go up to 850, and I think I'll make my y scale go by 50. Let's see if this looks like a reasonable graph, and oops, that's a syntax error. Where is that? Oh, I had an extra parentheses in there. Syntax error. Okay, here's the graph. Ooh, well, that looks kind of like what I was drawing. And here's something I could check. I could go second calc value. I'm going to use this for a number of things here. One thing I could check is, let's see if at 2.9, if I plug that in, do I get, I got 200. Great. At 5.1, I better be getting 800. Yes. So I'm pretty confident that this is the right equation for this situation because it actually produced the data that I was given. I can further use one way to get these values for 7, 8, and 9 and 10 years is to just keep using using that value. So I can plug in 7 and get 227. 227 foxes, rounding off to a whole fox. 8 is going to be 330. I'll round that to 338 foxes. For 10, for 9, that is 727 foxes, 727, and for 10, also 720. I kind of keep on writing that down. 720, what was that actually supposed to be? 727. I wrote it down twice wrong. So it should be 727. 27. Okay, well, another way I could have done that is, maybe an easier way, would have been to go to the table and to look through this and see, well, there's my 7 years and my 8 years and my 9 years and my 10 years. So that would have been an easier way to do it. Sometimes it's handy to do things like that from your graph and sometimes from the table. A third way to do that, if you want to just kind of explore some calculator methods here, as I can go to vars and yvars and choose that and do y1 of 7, and then I can do second enter and change the 7 to an 8, and I could do it that way. So there's many methods to quickly calculate those once you know the function, to quickly calculate 7, 8, 9, 10 years. The last part of this says that foxes are declared an endangered species when their population drops below 300 um, individual foxes. So between what two non-negative values of t? Well, non-negative values of t means, after we started counting them at time 0. What's the first time that they might become that they first become endangered according to this model? Well, that means uh, if I put in, here's 300, that's approximately 300 years. Here's what we're talking about here is the first non-negative would be, you know, this this part of the graph here. Well, what are the times associated with that part of the graph? Between what two non-negative values of t did the foxes first become endangered? That's what they're asking about, is right there. And one way I could do that is to set f of t equal to 300 and solve this algebraically. There's been several vodcasts about solving equations algebraically, and you should practice that some more if you're having a little difficulty with that. But that's not what we're going to do here. We're going to do this. I don't think we've really demonstrated how to do this numerically using your calculator, which is a really nice method. So I'm going to go back to the y equals menu, and I'm going to put in 300. That is a horizontal line at y equals 300. Here's what the graph looks like now. There's the graph, and I'm interested in those places where, just the same way on the graph on the board there, I can do that using second calc intersect. So I'm going to hit second trace button, and I get this menu. This is really a handy method. I press 5, and it asks me for the first curve. So I press enter. And then it bounces to the other graph, and it asks for second curve, and I press enter again. So those are the two equations that I'm going to find the intersection of. And then it says guess. And what you want to do when it says guess is move your cursor close to the place where you want to find the intersection. Well, it's going to find the closest one. So I press enter again, and it zooms right in on that point. So at 2.3 years, is the first time the population is going to hit 300 on the downward trend. So it's going to keep going lower after 2.3 years. So write that down, 2.3 years. 2.3 years. And then we find the other point here by doing second calc intersect again, and it asks for first curve, and you press enter, and you ask for second curve, you press enter, and you move your cursor over to another place where you want to find the intersection. Press enter, and it finds 3.49 years. So 3.4, I guess I could round that to 3.5 years since that was 2.3 and 4.9 years. So the answer to this question is, between what two non-negative values of t did the foxes first become endangered? Foxes were endangered between 2.3 and 4.9 years. And that's it. So that is how you get the information out of a word problem like this, graphing it, coming up with the equation, and answering some different kinds of questions about it. Okay.